Hello! I am rainbowed out today because it's one of my favorite things and it's finally raining again, and because this is our pre-lecture on the electromagnetic spectrum. What's that have to do with electrons? Well, it turns out everything. So the electromagnetic spectrum, we only see a small bit of it. We only see the visible spectrum. In case you don't know, and my son Joey is very fortunate because he was almost named this. So if any of you have ever gone through labor and delivery yourself, you know, yeah. So these are the color. Roy G. Biv, red, orange, yellow, and you know the rest. Green, blue. I, the most missed color, but is in my hat, but not in the right color. They put them in the wrong order, but we won't tell them that. They did it correctly in the scarf. So red, orange, yellow, green, blue, indigo, which is like this darkish blue, purple, right on the verge there, and violet. And again, these have to do with our chakras. So from our root chakra up to our crown chakra, and in my hat, it's reversed, which is really cool. So how we see a rainbow is white light. It was really bumming that I didn't have colored chalk and was too lazy to go get it. But then I was like, but I have white chalk. I have every color, because white is all the colors. In fact, if you ever watch spiritual teachers, they usually wear white because they're emitting. They're sending their love out to everyone. People will wear a lot of black, and the students will often laugh like the next week, and they come into class and they're all wearing black and they're like, yeah, I wear a lot of black. Black, dark colors absorb, and black absorbs all the colors. And so a lot of younger people will wear a lot of black because they think it's hip, but it's usually because they're depleted of energy. Anyway, a rainbow comes from the sun is all the colors of light. All the vibrations are happening up there. And when it hits what's called a prism, so a prism is a three-dimensional, right? That's my three-dimensionality, which is a raindrop. So that's our rain. When it hits a raindrop, it splits it into all the colors based on their wavelength. And so these are all different wavelengths, starting with red, which is the longest wave length, to violet for what we see, which is the shortest wavelength. That's just a symbol for wavelength. And so wavelength is how long the wave is. So how you see a rainbow is you have to have the sun behind you. This is you, or me. Let's make it me. Make my hair crazy. And I have to be looking that way. So the sun has to be behind me. So the shadow would be in front of you. It has to be raining. So the sun's behind you and it's raining in front of you and you look. So if you were in class with me, and this may happen during an office hour, because it might be raining and the sun comes up and you'll see your teacher disappear because she's pretty geeky about going to see rainbows. And this, Oregon, is like, gotta be the best place in the whole wide universe to see rainbows. And it will split out. And if you're really lucky, you'll see a double rainbow. And the thing that's really cool is it will go the opposite direction in the double rainbow. So the one ends with violet, the next one will start with violet. And if you see a triple, it will be opposite. So the first double rainbow I saw was when I first drove down the gorge coming to visit Oregon. It sold me. About 4 years ago, I was on a bike ride out by Barlow High School, and I saw a quintuple. I saw 5. I was hyperventilating, almost crashed my bike. You know, did the whole thing of trying to catch it, which, of course, you can't. Because there actually is, this is, okay, spoiler alert, I'm going to spoil rainbows. There is no end to a rainbow. There's no magic pot. Well, there is, well, not magic pot, that kind of pot, but anyway, there's no end to a rainbow because it's actually a full circle. And if you ever see one from an airplane, you will see. So it's the horizon that's stopping it from us seeing the full circle. So when we're looking at it in the horizon. All right, so a wave would be like that is a wave. And so the length would be either from peak to peak or trough to trough. And this would be a shorter wavelength. So this would be like our red, and this would be like our violet. So frequency would be me standing here and how often a wave passes you. So violet's going to pass me much more. So even though this is our shortest wavelength, it has the highest frequency. And our longest wavelength is going to have the shortest frequency. So they're always inversely related. As one goes up, the other goes down. And what's really cool is if you take the wavelength times the frequency for any wave, no matter what color, even the ones we can't see, you will get C, the speed of light. That's why it's called the speed of light. And they have broken the speed of light. It turns out every law, it was just a convenient way to do math. And then we realized there's a lot of exceptions, a lot. So what does this have to do with our class? Well, light doesn't have any mass, right? It's just waves. And this is what we as humans, we all see: red, orange, yellow, green, blue, indigo, violet, and all the shades in between. It goes beyond this. So again, this is the long waves. You should all know Roy G. Biv just because it's so cool. So beyond red is infrared. So that's why it's called infrared. So it's even longer. And they often call it as heat waves. A lot of medical offices will use it to keep a part of somebody's body warm. And beyond that is microwaves. So we're getting even longer. And what microwaves are special is these turn out, as we move in this direction, we then get into radio waves. So those of you who know what a radio is, these are all going to be ways of communication. And then we get to the ultra low frequency. So the lowest frequency that probably we can measure, I don't know. And this is where we get to the whales. This is how the whales communicate. That's my whale. So, you know, Dory and what was that? Finding Nemo and how she talked. So the whales are talking at a frequency way down here where their waves are like a kilometer long. These are in the 100 nanometers. So this is like 700 nanometers. And then it keeps getting longer and longer. Microwaves are really cool because this guy during World War II was working on communication, physics, engineering, something like that, with microwaves. And he happened to have a chocolate bar in his pocket. And he happened to be by the microwave. And he noticed his chocolate bar melted. And he went, huh, we all have microwave ovens now, which is a convenient way to heat up food. And there are some people who are paranoid about it. I've gone through my paranoia about it. And I've let it go because none of this is real. It's all just waves. All right, going past the short end, and we'll see why these are fine. What it is, what a microwave does is it's just the right wavelength when it hits a water molecule. And remember, we're 70-some% water. When it hits a water molecule, it makes it vibrate and it makes it turn and it keeps turning. And if you were vibrating and turning, you would warm up too. So as long as there's water present, the molecules are going to vibrate. The whole thing about the aluminum foil, and don't try this, if your aluminum foil was perfectly flat and had absolutely not one little dip or raise in it, the microwave would not spark it. So it has to have that little dip or raise for the wave to hit it. But don't try that at all because you probably can't iron it that good, and then you'll have the issue with microwave. All right, past violet is, of course, ultraviolet. This is where you go, ooh, danger, danger alert. In case you don't know, I talk about this in my Chem 106, the highest rates of breast cancer and MS, right, where you get the neurological muscle disease, are above the 45th parallel, which we are blessed to be in. It goes right through Salem. So 45th parallel is halfway between the equator and the North Pole, and we don't get enough vitamin D. Breast cancer is related to estrogen levels. Estrogen is a steroid, as is vitamin D, and we get into molecules in a couple weeks. And so we'll start learning and being able to understand a lot of this stuff. They've actually linked much, much higher rates of cancer to not enough sunlight. And right now, the whole coronavirus, depends what news you watch, and I watch a lot of alternative news, there's a huge link to any kind of cold virus and low vitamin D levels. Most people actually have low vitamin D levels. Your teacher got tested. I didn't want to be tested. She just was like, oh, let's just run a whole panel. And that was the only thing that came up. And I was like, huh. And so taking too much, I don't know. There's a lot of opinions out there. All right, what's after ultraviolet? We learned about these. So there's gamma. Remember the gamma rays? Some of you did. Those of you in my Chem 104. Gamma rays are beyond there. It means we're getting shorter and shorter and shorter. And actually, sorry, there's one in between, which is X-rays. And then past that, we get into the cosmic rays. And so why these are important is they have the short wavelength. They have high frequency. There's two symbols for frequency because everybody kept confusing velocity with the VU, the funky V sign. So they've changed it to this F. Anyway, shorter wavelengths, higher frequency, and then they figured out that not everything has the same energy. Turns out the frequency determines the energy or the momentum, well, energy of the wavelength. So the higher the frequency, the higher amount of energy. And that's, when they figured that out, that's when the whole quantum world opened, because that allowed us to talk, figure out about electrons. It was Max Planck who came up with the term quanta in the matrix, and Maxwell, who studied the electromagnetic spectrum and got that frequency and wavelength are always opposite, he made the assumption that they all had the same energy. And it was Max Planck who figured out otherwise. All right, you have some cool pictures in your notes that show you how big radio waves are, which is the size of a soccer field. And that size, like when you turn your radio to certain channels, so if you go to, if you go to the outdoor churches now, you get to do that. Yeah. Thing that's interesting is visible. We're in that range of the size of bacteria. Right. And then the bottom chart, it flips it. So just be careful. I should have just flipped it. And then you guys can read backwards. All right. So these are the ones that have high enough energy, even though none of these have mass. If you get to a high enough energy, you can knock electrons out of their orbit. And that's what quantum mechanics is all about. So once you get beyond violet, once you get to ultraviolet and beyond, they can suddenly have enough energy to knock electrons out. And they were like, well, how can that be? Because electrons have a mass. They're a particle. We can do measurements of mass. It's really itty bitty mass. But it's still a mass. These, they just cause rotations to happen and allow us to communicate and allow us to see beautiful colors. And so what happens is they've realized that electrons are vibrations. Electrons are that cusp between energy, light, the electromagnetic spectrum, and matter. You and me, you do matter. And Yeah, Niels Bohr, we talked about it with Rutherford's experiment. And so they were trying to figure out, how does the electron not run into the nucleus? They knew that the nucleus was where the positive was concentrated. And so in nuclear chemistry is a study of the nucleus. And so if all the mass is there, we found if an electron is that cusp of where energy is becoming matter, can you go back and E equals mc squared? If you have mass moving at a fast enough speed, you get energy. So we're all just different vibrations. And so the electrons move. Niels Bohr called them orbits, and all of his math was done with hydrogen, which has only one electron. We're going to look at it, looking at with all the different elements and where the theory is. And it's pretty interesting. Schrodinger, who won a Nobel Prize, he actually had to share his. He came up with a mathematical equation. So did Heisenberg, but nobody could follow his math. And Schrodinger went away for 3 days, came up with an equation. He took 2 pearls with him as earplugs. Like, who uses pearls as earplugs? But that's what the story is. And his mistress, apparently. And so the earplugs, he didn't want to talk to his mistress, went away for apparently the weekend and came back and had an equation. And somebody said, hey, that explains that periodic table that the chemists are all talking about. And he then spent most of his life, as did like Einstein, trying to disprove a lot of this stuff about the electron. Niels Bohr held his ground. And so that's where Albert Einstein's comment that God doesn't play dice with the universe, but apparently he does. Because everything that happens with electrons is all probability. It will probably happen, or it probably won't. Like, think of your cell phone. Is your cell phone going to work? Probably. Oh, except that moment. And what do? You can yell and scream and throw it, like a friend of mine did, and then broke his fireplace. Or you can say, turn it off, let the electrons reset, turn it back on, and voila, it works great. So I'm going to pause, and I'm going to do a demo for you. Just wait, I'll be back. I'm supposed to do the snapping. All right, we're back. I have a quick wardrobe change. Goggles on, ready to experiment. Still got my knock. Don't leave home without a knock. And we're going to do the rainbow experiment. We're going to turn the lights on. So, we'll see if I catch anything on fire, right? Look at the rainbow colors! Can you guys see them? So these are all chemical compounds. And every element on the periodic table, you see how the flame comes up there? That's how I caught a student on fire. Actually, I never caught a student on fire. I only caught your beloved teacher on fire. So the blue is copper. The orange, that beautiful, or the beautiful red. Can you see the red? I should have split them apart more. I won't know until we see this. But it goes red for strontium. The orange, can't remember. It's another one of the earth metals. And then the yellow must have been barium. Orange is also table salt. The green is boric acid, which is actually borax. Blue is copper sulfate, so root killer. And then the purple is potassium chloride. And let's see if we can get this one. This was just a mix of all of them because I wanted to see what would happen. I shot for extra credit. So to get the colors really good, you have to have something that's going to burn really hot. And that is methanol. So if you go to the store and say, I'm trying to find some methanol, they sometimes will think you're asking for meth, and they might call the police on you. But it's like the alcohol, O-L ending. So Home Depot carries methanol. It's what a lot of people use for cleaning. A lot of people have it in the garage. So you can actually also Google rainbow pumpkins, because a lot of people will make their pumpkins. So that's the bonus. Is carve a pumpkin in your favorite element. So it's hydrogen, but you're gonna have to get the full bonus, figure out what color your elements would be. So they each have electrons, and electrons are in orbits, and this is what a quantum leap is the electron jumps. We're gonna switch to this demo. That was the noise you could hear. All right, so this is the other part of the bonus. Oh, you can't see, I have a dinosaur here. I have a gummy dinosaur. I'm gonna drop my gummy dinosaur in there. From the color that you see, or maybe you don't see, oh, he's fading. He wasn't as dramatic as he was supposed to be. Anyway, and I know why he wasn't. I took somebody else's demo setup, and I don't think it was the right stuff. I think it was potassium chlorate instead of potassium perchlorate. Anyway, you did see a color. So which of these was it? So red is strontium. So whenever you see red fireworks, there is strontium in the fireworks. Orange is barium. Or sodium. So again, table salt will give you sodium, the orange's color. Yellow is calcium. The green is borax or boric acid. Blue is copper. Did not look green or blue there. Purple. Okay, I'm going to ruin this. Alert. So I guess you don't get a bonus. It was supposed to be purple. Did not look purple to me because it was potassium. So we might have to do a redo on that demo. Oh, and the bright sparkly ones were manganese. So as the electrons get excited with all the heat from the methanol, that's why it has to be methanol, because methanol gets super hot. The electrons get excited and they jump. So electrons exist in these orbits. And they can only be at orbits. They're called shells. And as the electron jumps from the heat, it will jump back. And oh, it may have jumped all the way out here. And it jumps further. And so, based on how far it has to jump, you get all different colors. So the electrons get excited, and then they come back. And when they come back, they don't mosey back. They can only be here or there. They can't be anywhere in between. So it's like on an elevator. You can be on the first floor, second floor, third floor. You can't be on the 2.394 floor. Actually, you could be. But we don't know that yet. We haven't reached there as humans. All right, many blessings. And I suppose your bonus question would be, what color is an electron? Until next time, bye. Bye-bye. We'll try that again. Bye.